Okay, so far everything we've done in the binomial theorem has been a strange coincidence. So yes, we have noticed that there's some sort of connection between Pascal's triangle and the coefficient of binomial expansions. We haven't proven that. So the binomial theorem comes into play here. So the binomial theorem is a formal proof that the coefficients of binomial expansions are have some sort of relationship between combinatorics. So we have, first of all, have the normal binomial theorem, which states that x plus y to the n is n choose 0 times by n choose 0 times x to the n plus n choose 1 x to the n minus 1 y, and so on. Or we can use sigma notation, so x plus y to the n is equal to the sum from k equals 0 to n of n choose k x to the power of n minus k y to the power of k. So some interesting properties of the binomial theorem are that we always sign the first value to be 0. So this is due to the property that n choose 0 is 1. And this is also because if we didn't set k equal to 0, then the coefficient of the last term would be n, and n choose n plus 1, which is impossible. And the most important property, number 3, is that the value of k is also the power that is given to the second term in the unexpanded bracket. This is extremely important because the coefficient of x cubed y to the power of 4 in x plus 7 to the 7 is 7 choose 4. So k equals 4, so the value of k is the power of the second term. So using that information to calculate the coefficient of... where did that go? Calculate the coefficient of x to the 8. We say, well, it's going to be 12 choose 8 times by 1 to the power of 4 x to the power of 8. So the coefficient is just 12 choose 8. This one here, it's going to be, well, we've got 4, so the value of k is 4, so 7 choose 4. X to the power of 3, so 7 minus 4, y to the power of 4. Part C, the coefficient of a to the 5, b to the 5. Well, it's going to be 10 choose 5, 2 to the power of 5, minus 3 to the power of 5. And part D, the term in a, n minus 4b to the 4, in a minus 2b to the power of n. Well, the value of k is 4, so n choose 4 times by a to the power of n minus 4 times by minus 2b to the power of 4. Okay. Find the coefficient, the specified terms in each expression. So we have to find x squared. So 7, it's choose 2 times by 2 to the power of 4 minus 2 is 5 times by x squared. Part B, well, the value of k is 5, so 14 choose 5 times by x to the power of 9 times by 1 on 2 y to the power of 5. Now, I am going to leave it like that, but you can simplify that. So part C, we've got, actually this is on the OneNote, we might fix that. So 7 choose 2 times by 2 to the power of 5 is 672x squared. This one here, 14 choose 5 times by 1 on 2 to the power of 5. I think it's 1001. Yeah, 1001 on 16, x to the power of 9, y to the power of 5. Okay, part C. So 1 on 2x minus 3y squared to the power of 11. Well, the value of k is going to be 1 because the only way to make y squared is to raise it to the power of 1. So 11 choose 1 times by 1 on 2x to the power of 11 minus 1, which is 10, times by minus 3y squared to the power of 1. That's equal to, well, 11 choose 1 times by 1 on 2 to the power of 10 times by minus 3 is minus 33 over 1024 x to the power of 10 y squared. Okay, this one says find x if the terms in x to the power of 10 and x to the power of 11 are equal. So first of all, let's do this. We know that 15, well, we're going to choose 10, and that's going to be 5 to the power of 15 minus 10 is 5, 2x to the power of 10, and that's equal to 15 choose 11 times by 5 to the power of 4 times by 2x to the power of 11. So that's equal to 15 choose 10, 5 to the 5, 2 to the 10, x to the 10, equals 15 choose 11, 5 to the 4, 2 to the 11, x to the 11. Cancelling out our x's, that dies. So we've got x is equal to 15 choose 10 over 5 to the 5, 2 to the 10, over 15 choose 11, 5 to the power of 4, 2 to the power of 11, which is equal to, I think we said it was 11 on 2. Yep. Okay. So we've got in the expansion of 2 plus 3x to the power of n, the coefficients of x to the power of 5 and x to the power of 6 are in the ratio 4 to 9. So let's figure out, first of all, the coefficient of x to the power of 5. Well, the coefficient of x to the power of 5, well, it's going to be n choose 5 times by 2 to the power of n minus 5 times by 3x to the power of 5. And then we don't actually need the 3x. We don't need the x because we're just looking at the coefficient. So times by 3 to the power of 5. On the bottom, the coefficient of x to the power of 6 is n choose 6 times by 2 to the power of n minus 6 times by 3 to the power of 6. And that's equal to 4 over 9. Okay, so there's a few different things we can do here. I'm going to realize that this is equal to 2 squared over 3 squared. So doing some cancelling, the 2 squared, we can take off 2 squared from here and then take away that from up here. And then we can take off 2 3s from here and 2 from here. And we're going to make that a 3 to the power of 4. So we've got 5 choose 2 times by 2 to the power of n minus 5 minus 2, n minus 7, 3 to the power of 5, over n choose 6, 2 to the power of n minus 6, 3 to the power of 4. And that's equal to 1. Doing some more cancelling, this will cancel with those. We've just got 1, 2 left on the bottom. So there's one more. N minus 6 is 1 greater than n minus 7. So that means there's just going to be 1, 2 left on the bottom. That's going to cancel. We're going to have 1, 3 on the top. So on the top, we're left with 5 choose 2 times by 3. And on the bottom, we're left with n, not 5 choose 2, sorry. That's silly. N choose 5. N choose 5. So n choose 6 times by 2 on the bottom, and that's equal to 1. Might keep going over here. So on the top, we've got n factorial over 5 factorial, n minus 5 factorial, times by 3, over n factorial over 6 factorial, n minus 6 factorial, times by 2, and that's equal to 1. So we can do some lovely cancelling here. That will cancel, that will cancel. The 5 factorial will cancel with the 6 factorial, and we're going to be left with just 6 on the bottom. This will cancel with this, and we're just left with n minus 5. So on the top, we've got 3 over n minus 5. And on the bottom, we're left with 2 on 6, and that's equal to 1. Multiplying the 2 on 6, we get 3 on n minus 5 is equal to 2 on 6. Cross multiplying, we get 18 is equal to 2n minus 10. And solving, we get n is equal to 28 divided by 2 is 14. Lovely. Okay, on to what we're doing on Thursday. So we stopped here on Tuesday. So use the binomial theorem to show that 7n plus 2 is divisible by 3 where n is a positive integer. Hint, write 7 as 6n plus 1. 6 plus 1. Okay, so we've got that 7, well, that's equal to 6 plus 1, and we're going to say that's to the power of n. And we're plussing 2. Okay, so let's consider the expansion of 6 plus 1 to the power of n. Well, the first coefficient is going to be n choose 0 times by 6 to the power of n plus n choose 1 times by 6 to the power of n minus 1 times by 1 plus n choose 2, 6 to the power of n minus 2 times by 1 squared plus dot 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 plus our last term is going to be n choose n times by 1 to the power of n. And then, of course, we've still got our plus 2 right at the end. So the general expansion of 6 plus 1 to the n is going to equal that. Now, some important thing to note is that all of this is divisible by 3 because there's a 6 in it. This is divisible by 3 because there's a 6 in it. This is divisible by 3 because there's a 6 in it. But this last term is not divisible by 3 because there's not a 6 in it. So we're going to say, okay, all terms except n choose n times by 1 to the n contain 6 and then thus are divisible by 3. But let's rewrite this sentence in terms of numbers that are divisible by 3 and numbers that aren't divisible by 3. So we've got our original expression, n choose 0 times by 6 to the n, plus n choose 1 times by 6 to the n minus 1, 1, plus dot dot dot, close bracket. Those were all of our things that were divisible by 6. Our stuff that's not divisible by 6 is n choose n 1 to the n plus 2. So this stuff is divisible by 6, the other stuff is not. Something to note, n choose n is 1. So we can rewrite this as n choose 0, 6 to the n, plus n choose 1, 6 to the n minus 1 times by 1, plus dot 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 plus, close bracket, sorry, I meant to close the bracket there, plus dot dot dot, close bracket, plus, well, if n choose n 1 to the n is 1, well then 1 plus 2 is equal to 3. Okay. We have already proven that everything in the brackets is divisible by 3 because it contains 6. And all of 3 obviously divisible by 3. So therefore, as n choose 0, 6 to the n plus n choose 1, 6 to the n minus 1 times 1 plus dot dot dot, and 3 are both divisible by 3, then their sum is also divisible by 3. So that's a little property that you mightn't have even seen since primary school. If you add two numbers that are divisible by 3, you result in another number that's divisible by 3. So, therefore, 7n plus 2 is divisible by 3. And that's our beautiful proof, QED. Now, interesting way of proving this using the binomial theorem. Just for your information, we really will never prove things like this using the binomial theorem. What we will use this proving idea to prove this identity using something that we call mathematical induction, or the principle of mathematical induction. And that's what that's one of the more common methods of proving divisibility. But this is an interesting one that's not really done in any of the other textbooks, so I thought I would include it. Okay. This kind of stuff, which we're doing next, it's kind of, I would say, an extension, because it's not directly in the syllabus, but it's something that is implied by the syllabus but not explicitly stated. So there's a few different rules that we're going to note. And the rules are that for whole numbers n, first of all, n choose 0 equals n choose n, and that equals 1. Also, n choose 1 and n choose n minus 1 are always equal to n. We know that's true. If I have the fourth row of Pascal's triangle, 1, 4, 6, 4, 1, we can see that the value, well, this is the 0th term, the first term, the second term, the third term, and the fourth term. We can see that the first term is the value of n, and n minus 1, 4 minus 1, is also 4. So that makes sense. There's also another identity that n choose 2, which is also the same as n choose n minus 2. That's due to the symmetry of Pascal's triangle, is equal to 1 on 2, n brackets n minus 1. Now, these are not on your formula sheet. It's something that kind of you can derive from these expressions using the idea that if you simplify n factorial, if you have n choose 2, if you simplify n factorial on 2 factorial, n minus 2 factorial, if you simplify it, you will get that identity. So it's something that's implied in the syllabus but not explicitly stated. So find the value of n if n choose 2 is 55. Well, we know that n choose 2 can be expressed as 1 on 2 n minus 1, and that's equal to 55. So n squared minus n has to equal 110, I think. So timesing the 2 up there and carrying out the n. So we've got n squared minus n minus 110 is equal to 0. Using the quadratic formula, n is equal to 1 plus or minus the square root of b squared minus 4ac. So 1 squared minus 4 times minus 110, which is 441. So the square root of 441 over 2, which is 21, 21. 1 plus or minus 21 on 2. So n is equal to 1 plus 21 on 2, which is 11, or n is equal to minus 10. So therefore, n is equal to 11, as in combinatorics, n has to be greater than 0. Or to be very formal, you could say as n belongs to the positive integers. So n has to be an integer, so a whole number, and it has to be positive. Okay, part B. Well, we know n choose 2 is 1 on 2, n minus 1. n choose 1 is n, and n choose 0 is 1, and that equals 29. So, timesing the 2 up, we got, and expanding out the n squared minus n plus 2n plus 2 equals 29 times 2, 58. So I've times the 2 up and also expanded out the n. So n squared minus n plus 2n is plus n plus 2 equals 58. Subtracting the 58, we get n squared plus n. 2 minus 58 is minus 56 equals 0. Using the quadratic formula, n is equal to minus 1 plus or minus the square root of 1 squared minus 4 times minus 56, which is 225. Not 255. 225, the square root of that over 2. Square root of 225, I'm pretty sure it's 15. Minus 1 plus or minus 15 on 2. So n is going to equal minus 1 plus 15 all on 2. So 7 or minus 8. So therefore, n is equal to 7 as n has to belong to the positive integers, or n is greater than 0. Okay. For the binomial theorem, obtain formula for n choose 0, n choose 1, n choose 2, and n choose 3. Oh, okay. Well, we already know that n choose 0 is equal to 1. We know that n choose 1 is equal to n. Part 3, we know that n choose 2 is 1 on 2n, n minus 1. Let's have a go at n choose 3. So n choose 3 is equal to n factorial over 3 factorial n minus 3 factorial. Let's do a bit of binomial expanding. Well, n factorial can be written as n can be written as n. What's going on? N factorial can be written as n times by n minus 1 times by n minus 2 times by n minus 3 factorial over 3 factorial times n minus 3 factorials. They will die. We've got n minus 1, n minus 2 all over 3 factorial, which is 6. And that's going to be our formula. n minus 1, n minus 2 on 6. So let's have a go at solving the equation. Part 1, 9 choose 2 minus nc1. Well, 9 choose 2 is just a number, so 9 choose 2 is 36, minus n choose 1 is n, equals 6 choose 3 is 20. Solving that beautiful equation, we should get n is 16. Part 2, n choose 2 is 36. That's just another one of those equations. So n choose 2 is 1 on 2 n. Was it n minus 1 or n minus 2? n minus 1. And that's equal to 36. So timesing the 2 up and expanding the n squared minus n is equal to 36 times 2, which is 72. So silly me. N squared minus n minus 72 equals 0. Using the quadratic formula, n is 1 plus or minus 1 squared minus 4 times 1 times minus 72, square root of 289. Personally, I would just probably go from here to the answer. If you feel like the quadratic formula is too easy, that's completely fine. So yeah, I would just go from here straight to an answer. But yeah. Anyway, I'm just going to do the full steps for our examples. So 1 plus the square root of 289 is 17. So 1 plus or minus 17 on 2 is equal to n. So n is equal to 1 plus 17 on 2, which is 9, or n is equal to minus 8. So therefore, n equals 9 as n must belong to the positive integers, or n is greater than 0. Okay, part 3, that's nice and easy. So n choose 2 is 1 on 2 n minus 1, plus 6 choose 2. 6 choose 2 should be 15, is equal to 7 choose 2. What is it? 17? I don't know. 7 choose 2 is 21. So, timesing up the 2 and expanding the n squared minus n plus 30 equals 42. So n squared, n squared minus n minus 30 minus 42 is minus 12 equals 0. So using the quadratic formula, n is equal to 1 plus or minus 1 squared minus 4 times minus 12 plus 49 over 2. So 1 plus or minus 7 on 2. So n is equal to 1 plus 7, 8 on 2, which is 4, or 1 minus 7, which is minus 6 on 2 is minus 3. So therefore, n is equal to 4, as n must belong to the positive integers. Beautiful. Okay. So for those of you who aren't here on Thursday, I need you to complete exercise 15C, or at least what questions I put on OneNote to do. But exclude 17B and 20C. I think it's because they involve calculus. I'm not 100% sure. I think that's the reason. But there would have been some sort of reason behind my madness. So anyway, yeah, hope that makes sense.